So we've talked about how muscles contract, but we haven't gone into what the fuel source is for muscle contraction. We mentioned ATP, but where is that ATP coming from? Or what's the main source of energy that we're using to create all that ATP? There's a few areas that we can pull from when it comes to using fuel sources. We can pull from the muscles. We can also pull from the blood. And in both muscle and blood, we can break down two different fuel sources for each that are going to be lipid-based and carbohydrate-based. So if we look at what's stored in the muscle, we have glycogen, which is a complex carbohydrate, and fat, which would be a lipid. In the blood, same kind of breakdown, except we have free-floating glucose, which is a simple carbohydrate, and fatty acids, which come from lipids. Now, when it comes to using carbs versus using fats, it really comes down to how long are you exercising, how long are you using those muscles. So let's look at this chart over here where we have how much time you're spending exercising in hours, so 0, 1, 2, 3, 4 hours, and how much of the energy that you're using, what's the percentage that's being used in which form. So we have this bluish kind of purple are the muscle triglycerides. So these are the fats that you find in the muscle. We have in this kind of pinkish purple color our plasma fatty acids, so our lipids coming from the blood. Down here in gold we have blood glucose. So this is the carbohydrate coming from the carbohydrates coming from the blood, and then in green here we have the carbohydrate glycogen in the muscle. And so what we see is over time we're going to use our glycogen in the muscles first. That's what we're going to use in that when we first start exercising. The majority of our energy expenditure is coming from that, and that's going to deplete over time. So we see it kind of shrinking hour by hour. And we see that the muscle triglycerides also shrink over time. So we're using up the reserves we have in the muscle first. And we're going to use up what we have in the muscle first, which makes sense if you think about it, right? It's right there in the muscle, quick and easy to get to, easy to access. We start using what's found in the blood in higher percentages the longer we exercise. So the longer we exercise, the more glucose we're using from the bloodstream, the more fatty acids we're using from the bloodstream. And so we're using up what we have stored in the muscle first, and then as we exercise for longer and longer periods of time, once we've depleted or we've started to deplete those muscle reserves, then we dive into what's free floating in the blood. There's a few pathways we can use to create this ATP. So we've used glucose or glycogen or fatty acids or fats or something, doesn't really matter in this case. But what pathway are we using to create that ATP? We can't store ATP for very long. It's a pretty unstable molecule, and so we have to kind of create it as we go in the muscle fibers. And there's a few pathways we can use to make this ATP as we're using it. We have the creatine phosphate pathway, or the CP pathway. This is the fastest pathway in order to make ATP, but it's a very short-lived pathway. You can't use it for very long. Same thing with fermentation. Very, very fast at creating ATP, but it's not very efficient. You get a buildup of lactate, and so it's another one that you can't do for very long. The CP pathway and the fermentation pathway, these are pathways that are good for quick bursts of energy, a quick burst of strength that you need, but not something you're going to sustain long term. If you need to do something that requires energy for a long period of time, you're going to use cellular respiration. This is aerobic, meaning it's going to use oxygen. It's not as fast as the CP pathway or fermentation, but it is a more sustainable pathway. So for example, if we were looking at two activities, we were looking at doing a deadlift and running a marathon, right? Both are activities that require energy, but the pathways are going to be different. If you're doing a deadlift, you're doing something that's really heavy, really strong, requires a lot of strength, but for a very short period of time. Creatine phosphate or pathway or fermentation are going to make sense. You need a lot of ATP very quickly for a very short time. But if you're doing something like running a marathon, where you're not at your peak speed, you're not using your muscles to the point of total exhaustion or to the max capacity, but you're using them for a very long time, aerobic activity or cellular respiration is going to be the source that you need, because it's going to sustain you for longer. Right? If we looked at Usain Bolt, right? He ran a 100-meter dash in under 10 seconds. That is crazy fast. The fastest marathon time in the world is just about 2 hours. So just kind of keep that in mind. A marathon, which is just over 26 miles, takes about 2 hours if you are the top athlete in the world. 100 meters takes you under 10 seconds if you are the top athlete in the world. If we were to take the speed of Usain Bolt and apply it to the marathon, the fastest marathon time would be about an hour. So you can see how the pace, right, is different. You can't sustain that sprint for an entire hour. You can't run 26 miles for an entire in 1 hour at that sprinting speed, because the pathway that you would use to do that sprint won't last long enough. It'll last the 10 seconds that's required for you to get through that 100 meters, but it's not going to last you over 26 miles. So something to think about, right? Depending on what activity you're doing, different pathways are going to be more beneficial than others. Right, and so we see here we have the creatine phosphate, right? We use that to make some ATP. We're very fast, but it's not very efficient. Glycogen, we use that to, we ferment that down into lactate, also produces ATP, but not very efficient. Both of these pathways, the creatine phosphate and the fermentation pathways, are anaerobic, meaning you don't need a lot of oxygen. So you don't have to sit there and kind of, breathe really heavy for a long period of time. You're not going to be using up oxygen the same way you would if you were running a marathon. Right, so both of these pathways, very fast, create ATP right when you need it for a very quick burst of energy, but they're not very efficient, and they're not sustainable in the long term. Over here with aerobic cellular respiration, we're using our mitochondria, we're using oxygen, produces a lot more ATP, but it is a little slower. So we can't use this pathway to do a quick burst of energy, but we can use this pathway when we need a longer term or longer, more sustainable pathway for some sort of activity we're doing that's going to take some time. And there's a few different muscle fibers that are going to rely on different pathways too. We have two different forms of muscle fibers. We have fast twitch and slow twitch. So let's look at fast twitch first. These fibers are going to rely on the creatine phosphate and fermentation pathways first. These are fibers that are adapted to help you with strength. When you stain them, they look very light in color, and they don't have a lot of mitochondria. Very little myoglobin, which is what's giving that staining, and they don't have a lot of blood vessels. So if you think about it, why there's very few mitochondria, why there's not a lot of blood vessels. Mitochondria and blood vessels are worried about bringing in oxygen, but they're using pathways that don't require oxygen, and so we don't have as big of a need of having a high level of mitochondria to produce ATP through cellular respiration. We don't require as much oxygen coming in because we're not using it in the mitochondria as much in the fast twitch fibers. In the slow twitch fibers, they do rely on aerobic respiration, and so they're adapted for endurance. You have to do something for a long period of time. They do have a lot of myoglobin, so they appear very dark due to that, and they have a ton of mitochondria because those mitochondria are the workhorses that are going to allow for that aerobic respiration. And because they're using so much oxygen, there's a lot of blood vessels because we have to bring that oxygen in through those blood vessels. So you think about which activities you would be doing depending on if you have a higher ratio of fast or slow twitch fibers, right? Fast twitch muscle fibers primarily are going to be using anaerobic pathways. They're great for strength, for sudden bursts of strength or power, but they do fatigue very fast because the pathways they use are not those long-term pathways, and we see them here in this light color, this light kind of lilac lavender. So this guy right here who's about to do a deadlift, who's about to lift this really heavy weight, he's going to be relying on his fast twitch muscle fibers. Whereas over here with the slow twitch muscle fibers, these are aerobic. They're using cellular respiration. They're not very explosive with their power, but it's very steady and sustained. So it's good for endurance. We see them here in that dark purple, right? And we see it demonstrated by this woman here who is running some sort of race, probably a distance race. She's doing 10K or 5K, or maybe she's running a half or a full marathon. Someone who is running a marathon would rely on those slow twitch muscle fibers. But regardless of which muscle fiber you have more of, or whatever kind of your situation is, you have to exercise. If you don't exercise, you're going to lose muscle strength, you're going to lose endurance, and you're going to lose flexibility. But if you do make sure that you have an active lifestyle and you're doing something, yoga, biking, walking, running, going to the gym and lifting weights, don't go to the gym right now, but going to the gym and lifting weights, those are going to help keep your muscles healthy, letting you maintain strength, letting you maintain endurance, and letting you maintain flexibility. And also increasing your cardiorespiratory endurance, so your ability to effectively pump blood and get oxygen around your body. It's going to increase your high density lipoprotein, which is your good cholesterol. We want that to increase. That's where we can actually make something with that cholesterol rather than deposit it into the cells and have it free floating. You also end up with a healthier ratio of protein to fat, so you have less fat content in your body typically and a higher protein content, higher muscle content. So your BMI will probably also become more of a healthy range, or enter into that healthy range if you're exercising regularly. Now that being said, you don't have to be a total Olympic athlete. No one's saying you have to go and train like Michael Phelps, but if you do exercise regularly, you will see, besides the nice appearance part, you'll see some really important health benefits, including the prevention of many cancers like colon, breast, cervical, uterine, ovarian cancers. We know that obesity is linked with a lot of cancers. If you're exercising and you're maintaining a healthy weight because you're working out, you can prevent, or at least lower your risk significantly of a lot of different cancers. Exercising actually improves the density of your bones. So if you're in that high risk osteoporosis group, if you're female, white, Asian, thin, you have a family history, anything of that nature, you know that you're at risk of osteoporosis and having poor bone density. Exercise can help combat that. That's why they say you need to be active, and that the sedentary lifestyle can contribute to developing osteoporosis. Exercise improves the density of your bones and makes them stronger. And then it also enhances mood and can help with depression. Now, that being said, is exercise a cure? No. If you have depression and you are prescribed a medication, take your medication as prescribed. But do consider the fact that exercise can help with your mood. So if you're feeling bad, or if you're upset at something, sometimes exercising can help relieve that stress and make you feel better. Sometimes though, people like to go a little too far with it, and that's where we get into anabolic steroids. Now, anabolic steroids, this is something a person would take to abnormally increase their protein production above what they would normally develop. There are problems with anabolic steroids. There are side effects, including high blood pressure, jaundice, which would mean your liver's not functioning properly, acne, and greater risk of cancers. So you're at a higher risk of developing a lot of cancers. If you're male, this can also cause impotence, and it can shrink the testicles. It can also lead to an increased violence and aggression in people, and lead to these very violent mood swings. So something to think about is, are they worth the risk? Should people be allowed to use these in athletics? If someone wants to be the best at hitting at home runs, that's fantastic. However, you want to think about not just the personal side effects of the high blood pressure. Maybe someone doesn't care if they die early of cancer, as long as they get to live in the record books. However, if it increases the risk of violence, and aggression, other people will be affected by that. So something to think about when you are reading about steroids and you hear people talking about whether or not they should be allowed in professional sports, think about what the real risks are of someone taking them. Let's go to the opposite side of the spectrum though, where muscles have problems. There's common kind of run-of-the-mill muscle disorders and issues, and then there are more serious muscle issues we'll get into. But let's start with the more common ones that you probably have experienced at some point in your life. So things like a spasm, this is where suddenly your muscle just involuntarily contracts and it can be painful. Convulsion would be multiple spasms of a skeletal muscle. And then a cramp is kind of like a specialized name for spasms that are very strong and powerful. And a lot of times you feel it in your leg or your foot. So if your foot is all cramped up, it's because your muscles are involuntarily contracting to the point where it is hurting you. There's also strains and sprains. Strains are focused on the muscle itself, where you have overdone something, you've overstretched, or you've actually maybe even torn a muscle a little bit. The sprain involves the muscle and all of the surrounding parts as well. So the ligaments, the tendons, the blood vessels, and the nerves. So you've twisted a joint, you've rolled your ankle, you've moved your knee wrong, and not only are the muscles injured, but the ligaments, the tendons, the nerves, the blood vessels might be injured as well. So strain is less involved as a sprain. Right, and those are all ones that, again, you probably have experienced at some point in your life, but they're not too crazy. You can get over them relatively easily. Some diseases involving the muscular system include myalgia, fibromyalgia, muscular dystrophy. Myalgia, this is when you're achy, you feel really achy. It could be because of an injury or infection. This is something that can pass. So once the injury is healed or the infection is passed, more than likely your muscles won't ache anymore. Fibromyalgia, though, this is something that's less well understood. This is where you have that achiness, but for a long period of time. So it's chronic. We're talking long-term achiness. It's not associated with a known injury or infection. In fact, with fibromyalgia, we really don't understand it very well. Most people end up getting diagnosed after they've eliminated a ton of other conditions instead. So it's kind of something that takes a long time to diagnose because we don't really know much about it compared to other illnesses and other diseases. Muscular dystrophy, this is something you are born with. It's a genetic disorder, in which case the muscles are not able to maintain their strength. They're going to break down, they're going to weaken, they're going to degenerate. And so a person with muscular dystrophy would find over time their muscles would waste away and they would start to lose muscle function. People who have muscular dystrophy, depending on how severe their case is, depending what kind they have, can die early. So something like Duchenne muscular dystrophy, which is a very particular one. Most men who have it, since it pretty much mainly affects men, most men who have it will live to be about 20. At that point, then it has damaged the muscle so much that things like breathing become laborious, become very difficult, and eventually they can die from it. Myasthenia gravis is an autoimmune disorder. So remember, autoimmune, your immune system is attacking the healthy tissue of the body. And so in this case, myasthenia gravis is where the body, the immune system, is attacking the acetylcholine receptors. If the acetylcholine receptors are damaged, it doesn't matter how much acetylcholine is released by the neuron. The muscle is basically deaf to the message being sent by the nervous system. It can't listen to that message, and so the muscles never receive, they never fully understand the signal to contract, and so they don't. And that leads to a weakness of the muscles, especially in the face and the neck and the extremities, like the arms and legs. ALS, or amyotrophic lateral sclerosis, this is also known as Lou Gehrig's disease. This is a motor neuron disorder where the motor neurons, meaning the neurons that lead to your muscles and talk to your muscles, are going to degenerate and die off. And when those neurons die, there's no way for the rest of the nervous system to talk with those muscles. So the muscles don't ever receive the information. They're never told to contract. And so a person with ALS would slowly lose voluntary muscle movement. And again, one of the common issues is the diaphragm not being able to allow that person to breathe. This is something that can happen pretty fast. Most people who are diagnosed usually end up passing away from it within a few years. There are some exceptions. Stephen Hawking is a good example of someone who is an exception who lived a very long time with it. But for the most part, someone with ALS does not have too much time left once the diagnosis is hit, because those motor neurons get attacked and degenerate pretty fast. Sarcomas, you see that OMA tells you it's a cancer, so the in sarco tells you muscle, so this is a cancer involving the muscle or connective tissue associated with muscle, so it could be something like a tendon that's affected, but that is some sort of cancer involving some portion, some part of muscle or something associated with muscle. Moving on to our absolute favorite thing, homeostasis. How are we maintaining homeostasis? And we're looking at the skeletal and muscular systems together because they're really intertwined in maintaining homeostasis. They're both involved with movement, and that movement allows us to maintain homeostasis because it allows us to respond to stimuli. You know, if it's really, really hot outside, you can walk to a building that has air conditioning, right? That would be a response to stimuli. Or if you see something being thrown at you, if you see a baseball thrown and it's flying towards your face, you can respond to that with movement. You can catch it or you can duck. Digestion of food, right? Our ability to move food throughout our digestive system. Returning blood to the heart. The muscles are going to help kind of push blood up through those veins. They're going to give some assistance to those veins of getting blood back up to the heart. And they're also going to help with moving air in and out of the lungs. You think about the diaphragm and how the diaphragm and the intercostal muscles between the ribs allow that chest wall to change shape, to allow that volume inside the chest cavity to change, and that's allowing us to get air in and out. We're also providing protection. Think about bones like your rib cage protecting the heart and the lungs, your abdomen, your abdominal muscles providing protection to your digestive organs. Those are pretty important pieces that you don't want to just get squished around, and so the muscle and the bone are going to help provide some level of protection. The muscles are going to be, and the nerves need calcium, and the bones help serve as a reservoir for that calcium, so they're working together to maintain proper levels of calcium. All those blood cells we talked about are made in the bone, so having bone there to serve as a factory for blood cells is extremely important. And then the muscles help maintain body temperature. If you get really, really cold, or you walk out and it's really, really cold out, you start to shiver. That shivering, those little tiny muscle contractions are happening so you can generate some heat so that you can warm yourself back up. Right, if we look at how we interact with some of the other body systems, some of this is stuff we've already mentioned, but we're going to go into it again. Again, we're maintaining blood calcium levels with the skeletal system, and the muscular and the nervous systems both rely on that. Cardiovascular system relies on the muscle contraction to keep blood moving through those veins, and the skeletal system is going to help by producing the blood cells for the cardiovascular system. We have smooth muscle to help with the urinary system to move move fluid through the entire urinary system, and then in turn the kidneys are going to help bring back in some of that calcium that we need for the muscular and the skeletal systems. The digestive system relies on muscle to move things throughout, so we go from very start to very end. The endocrine system is going to assist the muscular and skeletal systems by providing hormones that are going to stimulate growth, and also some of the hormones required for calcium in the blood to maintain levels of calcium in the blood. The respiratory system relies again on muscle to help with breathing, those intercostal muscles and the diaphragm. And then the reproductive systems need muscle contraction to move gametes. So when you move an egg or sperm around, you need muscle to contract to move those. And then for those who've had children, you're very familiar with uterine contractions, and that's all due to muscle as well. I mean, you probably aren't a fan of it, but it was something that helped to get that child out of your body. And then androgens and some of the sex hormones are going to help promote muscle growth as well. So they're going to be sending that signal to the skeletal and muscular systems to say, hey, it's time for you to grow, especially around that puberty time.